Hello and welcome everyone. Welcome to the module 4.4, and in this we will learn about the hypothesis testing. Hypothesis testing is very important in any kind of statistical analysis that you are doing to test whether whatever hypothesis you are making are significant or not significant. That helps you to interpret the results, help you to convey the results in the way so that you understand the significance of the results, significance of the data that you are presenting to the anyone, to your organization, to your colleagues, to your team members. So understanding the basics of hypothesis testing is very, very important. So let's cover this. So again, hypothesis testing is like a lot of terminologies you will hear here from myself. Like you can do any kind of test, you can do t-test that we learn, you can do chi-square test, you can do, but at the end what you will get the p-values. P-values will tell you about the significance of the test that we have done. P-value can be computed by considering the type 1 error and type 2 error and considering the statistical power. So you need to understand few things. What is type 1 error, what is type 2 error, what is the statistical power, what is the p-value, whether the data and test you have done here are significant or not. So that will help you to make decision based on the data with proper statistical reasoning, not by just saying that okay, I am seeing the differences between two groups, but you need to say okay, the differences in these two groups are significant enough with this much statistical power while considering the type 1 error and the type 2 errors. Here are a lot of things that you will learn. You will learn about the formulas, what is h0, what is h1, like what is null hypothesis, what is the alternative hypothesis, then how to select the right test to test between the null hypothesis is true or the alternative hypothesis is true. Then the type 1 type of error, which is important to consider or important to calculate the power of the statistical test that you are performing. If you will get the type 1 error, which is alpha, then you can compute the statistical power by computing the beta also. Then how to interpret the p-values, significance, and the effect sizes for that statistical test, and to perform the t-test and the chi-square test. So for testing workflow, a systematic approach is to pose a hypothesis. So we say that there is the hypothesis, null hypothesis, and then there is an alternative for any statistical test. Before you start, if you are comparing two groups, let's say disease versus healthy, okay, if you're comparing these two groups, your null hypothesis is always that there is no difference between these two groups. That is your null hypothesis. Then your alternative hypothesis is there is a difference between these two. You need to reject the null hypothesis to prove those differences are correct and there. So H0 typically represents the no effect and the no differences. Then you will go for the test and selecting the statistics. Let's say you will select the test, t-test, chi-square test, ANOVA test based on the data, based on the distribution, based on the inference that you would like to make, based on the intervals, confidence intervals, and the data distribution that we have seen. Based on the data types, distribution, research questions, a lot of things comes into the picture. You decide which test you are going to perform here. Then you will define the significance level, that how much significance you want, how much error you can consider here. Okay, so you want like 95% of the accuracy, you want 5%, 0.005% of the 95% of the significance level, or 98% of the, or 99% of the significance level, you can define here. Then you will compute the p-value. P-value is simply calculate the test statistics, determine the p-value, which is probability of observing the data as extreme as yours if h0 is true. So you are getting the probability of observing data as extreme as yours if h0 is true. So ultimately you are trying to identify what is the probability of observing. The minimum the probability is, the higher the significance is. Okay, minimum the probability and higher the significance, because you are considering your h0 is true and now you are going to reject that hypothesis. So if we'll compare the alpha that you are getting, if probability is lesser than alpha, then you reject the null hypothesis, which is h0. That means your results statistically significant results. When your p-value is greater than alpha, then you fail to reject the null hypothesis. That means whatever evidences you are collecting, whatever statistical test you have done is not significant enough to reject the null hypothesis. So this is the concept of the p-value in total. It's all about rejecting or accepting the null hypothesis. You draw a conclusion like on the basis of interpretation of the results based on the research questions. You define that, you report the effect size, you report the confidence interval that we have discussed in the previous module, how to detect the confidence interval from the variance or from the population. For the critical significance, you report the effect size, you report the confidence interval, and you report the p-values. Now at the end, you verify and document. Verify assumptions were made, document all the decisions, include pre-selected alpha levels and any kind of transformation that you have added in the data. Statistical significance doesn't necessarily implies the practical importance. Always consider, so in sometimes you will get the statistical significance, but your effect size is not big enough to say that whatever statistical significance you are getting is with high or strong confidence. And your domain of context also vary. So we cannot solely rely on p-value, but p-value is a great idea to test the significance of any kind of test that you would like to perform. Okay. Then you go for one sample t-test. There is one kind of t-test that you do. So this is a simple test statistics. In sample test statistics, you are trying to compare the sample mean to the hypothesized population mean. So you have once your sample mean, and then you have a hypothesized population mean. So this is your sample mean, actual mean, hypothesized population mean, and then you are getting the standardized by the standard error at the bottom. So you are dividing by the standardized standard error, and considering the degree of freedom, which is n minus 1. By doing this, you get the t values, t statistics, statistical value for this particular t test. You can compute the confidence interval. We have discussed computing confidence interval. There are n number of ways. Here you can use the population mean. Reject h0 if mu 0 falls outside that particular confidence interval. Now instead of p values, if you're getting the confidence interval, you are rejecting the null hypothesis if the value that you are predicting, if the value you are getting is outside or beyond the confidence interval, either higher or lower. Okay, then you do the effect size. Effect size, it standardizes the mean differences. Smaller effect size, medium effect size, and there is a large effect size. Larger effect size means you have a strong assumptions or strong variability on the date, on strong certainty of the data that you are reporting. So effect size, if the effect size is higher, you can rely more on the statistical results that you are reporting in the data. Check always the assumptions, normality for small samples, no extreme outlier, random and independent sampling if they are affecting the confidence interval or test statistics or the effect size in any way. There are other type of test also, two sample and pair t-test. There are independent t-test and the dependent and pair t-test. Independent t-test is comparing means from two independent groups. When you're comparing the diseased individuals with the healthy individuals, that's it. The purpose is to different subject in each group. Assumption is either equal unequal variance. Example is you are considering the comparing the drug or placebo group or anything. The ultimately those observations are completely independent from each other. But when you go for pair t-test, you have the purpose of differences between the paired observations. Paired observations can be anything, like you are getting the observations in individuals from different time or like in timely manner. You are collecting the multiple samples from the single individual. The same thing you are doing for the multiple sample collections for the different individual. So for same individuals you have at the different time points. So the observation you are making here are not completely independent from each other. The observation is coming in the second time point can be dependent on the observation in the first time points also. So in these kind of sample sets, in these kind of data sets, you go for the paired type of t-test. You design same sample, measure twice, thrice with the matched pairs. Advantage is controls individual variability, and this is more powerful because when you are comparing two individuals or two groups in which you have an individual which you are comparing with the another individual, this individual was measured at multiple times. So that means it control the individual specific variability, and it can provide more meaningful, more powerful result than compared to the independent t-test. It can, there can be many example before or after treatment, twins studies, longitudinal sampling, lot of things can be done in the pair t-testing. So you just decide what kind of testing you want to do, whether impaired t-test like independent t-test or the pair t-test. Then there is a test called chi-square test. Chi-square test, generally we say goodness of fit, like observed versus expected. Here independence is the contingency table, expected outcome can be greater than 5. For instance, chi-square test statistics you can get by the observed frequency and the expected frequency. So you can get the observed minus expected divided by the expected frequency, and we'll take a sum. You will get a chi-square statistics, and this will be for all the instances. You will repeat this exercise again and again. What is your observed frequency, what is your expected frequency divided by expected frequency for one instance, second instance, third instance. You will keep it doing, do it sum and get the chi-square test statistics. You can get the expected counts also. The expected counts is the from the independent test. Expected count is total row from the I, column j from the total, and there is a grand total. So by using this calculation you can get the expected count of contingency table for all the instances you have. Then you can compute the degree of freedom. Degree of freedom is always like, for independent test, for goodness of fit, computing the degree of freedom is very uh, great idea. Once you get the degree of freedom, you can use this degree of freedom for computing the test statistics. Chi-square approximation may be invalid if you have a more than 20% of the expected columns are less than 5. Okay, so those kind of things are variable based on this test to test. Those numbers you can just remember what kind of test you want to do. Now here is a very important concept of type 1 error and type 2 error. So type 1 error, if you will see, if h0 is true, let's say we are saying h0 is a null hypothesis, that means we are expecting there is no differences. H1 is the h1 distribution we are seeing here. H1 alternative hypothesis when there is differences. So type 1 error is when reject h0 when it is true. Type 1 error will always be there when we are rejecting the null hypothesis. We are saying that is there a difference between group A and group B. Our null hypothesis is h0. Okay, what we are predicting after doing those statistical tests, because we are saying, okay, there is a difference between group A and group B, but actually there was no difference. So this is a type 1 error in which we are rejecting the null hypothesis, which was actually true. Null hypothesis was actually true, but we are rejecting it. So this is a type 1 error. That means you are mispredicting anything that is actually not happening. You can say this as a false positives also. Like you are saying group A and group B are not different, it is your null hypothesis and it is true also, but you are applying a test and you are finding, okay, there is a difference based on the statistics you are reporting. So this is false positive. This is a type 1 error which lies somewhere here. Okay, then you can get the type 2 error. Type 2 error is fail to reject. So that means actually in the data there is a difference between group A and group B. Actually there is a difference, but your null hypothesis is there is no difference. You want to reject this. By doing this statistical test you should reject this null hypothesis, but when you do this statistical test you are not able to reject this null hypothesis based on the p values you are getting. That means you fail you fail to detect whatever is there. Okay, so that is your type 2 type of error, and those are the false negatives for you. Means like those should be positive but you are detecting as a negative. So those are the type 2 error. These two error type are very very important. Type 1 error are a false positive when you reject the true null hypothesis. Type 2 error are a false negative when you fail to reject the null hypothesis. Okay, power you can compute for the data anytime by computing 1 minus b, that is 1 minus type 2 error. Whenever you will do 1 minus type 2 error you will get the power. Test sensitivity trade-off, reducing one error type increases the other. If you will reduce the type 2 error, type 1 error will increase. If you will reduce the type 1 error, type 2 error will increase. Okay, those are the fine balance that you will learn between the sensitivity specificity. We make the ROC plots, those kind of things. Then we go for the power analysis basics. For the power analysis there is a inputs which is a significance level that you want for the power. So power analysis ultimately is, let's say if I want to compare two populations and now I don't have the data, I don't have the sample set, I need to go and collect the sample set. So there, how much samples should be more than enough for me to test my hypothesis? That is a power analysis. So for that you set your threshold, like how much significance level you want, how much desired power you want, then how much effect size you want, and how much is the variance in the data. Then your output will be the sample size. It will give you the analysis that you will do based on the desired significance level, desired power, effect size, and variance. It will give you, okay, you need, let's say 200 of the samples to get this kind of a statistical significance that you needed to represent the entire population. So that is power analysis. Power analysis you do before starting your study, and that's like very powerful way and very statistically significant way to come up with these some specific number of samples those are required to do your downstream analysis, and you select your samples based on that power analysis and you use that for your downstream analysis and supporting that analysis. Trade-offs: larger alpha, larger significance level, higher power, but more, it can give you more type 1 error. Like it can be larger significance, it can higher power, but it can give you type 1 error. Means like it will falsely detect the differences, it will falsely reject the null hypothesis, and we don't want to do it a lot also, depending upon the questions, depending upon what you can afford in that particular data sets, what is your like top priorities, whether you can focus on, whether you should focus on type 1 error or type 2 error, uh, on those data sets, those kind of questions based on the decisions that you want to make based on those predictions. Larger the effect size, easier to detect. So if the effect size means the differences, the stronger the differences between two groups, you need to require a minimum number of n, minimum number of sample size, to get the desired number of power or desired number of statistics. Effect sizes you can compute for the numerical data, for means, or for the categorical data. For the means, you can get the mean differences in the standard deviation. That is the Cohen's tree, and that is the effect size for you. Like for two groups that you are comparing, group 1 or group 2, if we'll get the mean of group 1, mean of group 2, and we learn how to get the mean, and if we'll get the differences between these two groups, the mean of these two groups, that is your effect size. Stronger the effect size, that means you need less number of samples to get the desired statistical results. You can adjust for the small samples, less bias than the d values, Cohen's d, that is Haig's g. Sometimes you use the effect size, not the Cohen's d but Haig's g. It has a flexibility to adjust for the smaller sample size also. Then you get the r square variance explained, and it is very very important. Higher the r square value, that means higher the variance explained by the test that you are doing. And context is independent intervention. Large effect size varies by the field. When you go for the categorical data, so you identify differences in the proportions. Now you get the proportions for the group 1, proportions for the group 2, and then you get the differences between these two proportions, and you get the odds ratio. So this is very very important here. Like depending upon what kind of data sets you have, you will use certain things. You will use mean when you have a continuous data, you will use proportions when you have the categorical data. Then you will compute the odds ratio. From the proportions, you can get the odds ratio, which is widely used in the medical research, like log 2 fold change, log 3 fold change, log 4 5 fold change, and then p values. The consistency table generally range from 0 to 1 for the correlations. You always report the confidence interval along with the odds ratio, along with the p values that you are reporting, so that you communicate effectively the uncertainty that might happen during the tests that you have performed. Now it's all about p values and confidence interval. P value is not is equal to the probability of h0 true. Just measure the evidence against h1, h0. Like p value is always measuring the probability, what are the chances that the null hypothesis is not true, or like probability of checking that alternative hypothesis is true. So it is always trying to reject the null hypothesis. Confidence interval conveys the magnitude and the uncertainty. So whenever you report the confidence interval along with the p values, so that means you are covering the uncertainty in the data, you are focusing on the effect size. 95% of confidence interval excluding the null values, p values less than 0.005 for two side of test. Those kind of things can be the ideal things to report in the statistical data, and so that your statistical test, whatever you are reporting, is significant. Pre-specifying the alpha significance level analysis plan. Avoid p hacking and hack and rank. Like don't play with the p value by simply changing some of the data values, some of the imputations. Try to specify your significance level before, and make an analysis plan depending upon the study, depending upon the questions, depending upon what kind of test you want to use, based on the data distribution and all other things you have seen. There are many examples. Two sample t-test you can do. Two sample t-test, if I will simply take an example, if define the hypothesis and then check the assumption first. So hypothesis is no difference between two methods first, and then there is two-tailed and one-tailed method, in which if you are not selecting the hypothesis, we are rejecting the hypothesis, that means the alternative hypothesis is true. You're checking the normality by QQ plot, independence, and calculating the variances. So for group 1, let's say you are getting the mean for the group 1 is 82, mean for group 2 is 77, then the standard deviation of 6.3, 7.2, and the n1 is 28, n2 is 25. Then you get the t statistics degree of freedom, which is around 49, rounded to 49, because how many samples you have, it depends on that. You can compute the degree of freedom. Here you will subtract the mean 1 from mean 2, and then you will go for each sample. So for each sample you will get s1 square divided by n1, s2 square divided by n2, and that's how you will do completely from end to end. And by doing this, you will get some kind of t statistics, and from t statistics, as I described earlier, from the significance level, critical t value you will compute, and from critical t value and the significance, you will get the p-value. So here the p-value you are getting is 0.001, that is less than 0.005. That means your differences between two tests you are doing is significant. So you can reject the null hypothesis. Decision is you are rejecting the null hypothesis. Your effect size is again the mean minus mean divided by 6.7, which is a medium and large effect size. In total 95% confidence interval of mean difference is 1 and 8.4. So 8.4 will be the lower quartile and 1 is the higher quartile. If you will go out of this, then the prediction might not be true. So these formulas are very simple. You ultimately you are taking the mean of one group, mean of another group, and trying to find out the differences. The differences are statistically significant or not, whether it will be able to reject the null hypothesis or not, and then you get the effect size and the confidence interval. Now chi-square, you have the contingency table. You have treatment 1, you have treatment 2, improved, no changes, and total. So in the treatment 1, there are 52 individuals who are showing the improved performances, 18 no improved. Treatment 2, there are 28 and no change in 32, total 60. Now you would like to see the differences between treatment A and treatment B. So you are computing the expected frequencies. So E is equal to raw total into column total divided by grand total. So treatment A, the treatment A is the improved is 60 multiplies by 70 divided by 120. So what you are doing for treatment A is row total is this, the column total is this, and divided by the grand total. Grand total is 120. So for treatment A, improved is 35 because you're doing the test. For treatment A is no change. Again, for no change, if you will go, then it is row total, no change, row total, then row total will remain the same, and then the column total, which will be 50 here, and the total, the complete total. So you will get the 25. Then treatment B, again row total. For treatment B, row total is 60 divided by column total. For treatment B, for improved, if you like see, this is 70 divided by 120, it's 35. The same for treatment B, no change. Again, for no change, row total will remain the same, the column total will be 50 and divided by 25. So for treatment A, the improved value is 35, no change is 25, treatment B improved is 35 and 25. Now you can calculate the chi-square. For chi-square, you can use the long formula here, which is written here: observed minus expected divided by expected. So what is observed here? Observed is 42. What is expected? Expected is 35. This is expected frequencies that you are computing here. 35 divided by expected frequency square. So you will do this for 42, for 18, for 28, and for 32. So observed minus expected square divided by expected. This is the simple formula that you do here, and you can compute the chi-square statistics. Ultimately, you will get the chi-square statistics, then you will interpret the results. Chi-square statistics is very simple. First, you will get the confusion matrix. From that confusion matrix, you simply need to compute the expected frequency for each observation that you are making in the confusion matrix. Once you have the expected frequencies and actual frequencies, you do actual minus expected divided by expected, the formula. Interpret the result. Df is equal to 1, critical alpha is 0.05, is 3.84. Since 6.72, the value that you are getting is greater than 3.84, we reject the null hypothesis. Whatever you are getting is greater than the expected statistics is greater than value, you are rejecting that. You can get a standard deviation. Treatment 1A improved 1.18 more than the expected. Treatment A, treatment B no change plus 1.40 more than expected. Again, for treatment A and treatment B, for both, it is always more than expected what you are getting. So ultimate conclusion here, you can make the significant association between the treatment A type and the outcome, specific treatment out and out. Summary checklist. You will go to the hypothesis testing for best practice, align the test selection, base the research design and the data characteristics, then verify the assumptions before drawing any kind of conclusions. Report the effect size, report the confidence interval along with the p-values. Consider the statistical power and the required sample size during your planning. This is very important when you are planning any kind of experiment. Compute the statistical power, do the power calculation first for the observed significance that you want, observed effect size that you want, those kind of calculations to come up with the appropriate number of sample size to do the desired statistics. Be aware of the multiple test issues. If you're doing t-test or chi-square test or pair t-test, unpaired t-test or Wilcoxon test, know about the things, what test has what kind of advantages and disadvantages, whether it is fitting with your study, whether it is fitting with your plan, and you can make those kind of decisions. Now quick check, what measure is more informative than p values alone for understanding practical significance or in hypothesis testing? You can see the effect size when when you're using the category numerical variables. You can compute the Cohen's d for differences in proportions, or you can use the odds ratio in proportions. You can use the odds ratio when you're working with the categorical variables. This is a simple check. I hope we have covered each and everything in the hypothesis testing in this module. We'll move to the another module, that is module 4.5. We'll learn about the correlation versus causation. Stay tuned.